So in this video, we will start with the introduction to a system, which is within a grand canonical, which can be categorized within a grand canonical ensemble. And hope you remember the meaning of grand canonical ensembles. So in simple words, I should tell that these are the kind of ensembles in which you allow simultaneously the exchange of particles and the exchange of energy between the microstates or between the elements of a system. So that is how you simply define a grand canonical ensemble. So here we have to, unlike the case of canonical ensemble, here we will have to consider the changes in the number of particles also. And if you remember the kind of derivation which we did for the canonical ensemble, this is here in grand canonical also, it is pretty similar. Okay, so I would suggest that you remind yourself of the derivation and the beginning derivation of the canonical ensemble before getting into grand canonical ensemble. So in my derivation, I will be assuming that you are remembering those kind of ideas which we introduced as part of that. So what was the beginning of that derivation? We did assume a system, right? So here also we assume a system, and within that system you assume an element A, right? This is how we started there also, right? So here within that I assume an area, assume an element, sorry. I assume an element. What should I name it? Let's continue. The A, right? That's how. So I called this element A, but here we have to express it in terms of NR and the ES, because since this is a grand canonical system, an ensemble, we do allow the number of particles and the energy to change or to be exchanged. So A of NR ES. In actual terms, it should be written as A of NR V T ES, right? So this is the exact detailed explanation of that. And we assume that this system A is placed within a reservoir A dash, NR dash, ES dash. So this is just similar to what we assumed in the canonical ensemble, right? And this system will have a common temperature T, and what else? I can always define more into this system as NR plus NR dash is equal to some kind of total number of particles, right? N0. And this will be a constant. Why? Because we do allow the number of particles and energy to exchange between the elements of an ensemble, but this whole system is protected or isolated from the external atmosphere. So therefore the N0 is a constant. So NR plus NR dash is equal to N0 is a constant, and ES plus ES dash is equal to E0, that is also a constant, right? And this ER can of course vary between E0 to 0. Sorry, ES. ES. And similarly, this NR can vary between N0 and 0. So those are the conditions which should be obeyed by these systems. So that is for the system A, and for the system, for the reservoir A dash, you have the similar conditions. ES dash will vary from 0 to E0, and NR dash vary between 0 to N0. Right. So these are the conditions within which we work. And another assumption, if you remember, which we did for the canonical ensemble, similar to that here, I assume that the NR is much smaller compared to N0, right? Or NR by N0 is much less than 1, and ES by E0 is also much less than 1, which also means that my NR, right, is much smaller compared to NR dash also, right? Whatever is being left between N0 and NR is NR dash. So since NR is very small, which means that similar to N0, NR dash is also very big compared to NR. Okay. Now we have to write the probability equation, right? So let PRS be the probability for the system A to be in any one of the microstates characterized by energy ES, okay, and number of particles NR. So PRS is the probability for the system A. What is that system? Actually, it is an element. So probability for the element A to be in any one of the microstates characterized by the energy ES and number of particles NR. So that is the probability, and therefore I can write PRS is proportional to omega. What is omega? Omega is the number of particles, number of microstates. So PRS is proportional to omega of NR ES, right? But you remember that we can assume just similar what we did in the canonical ensemble. Here this can be considered also to be proportional to omega dash NR dash ES dash, because this makes it more prudent and more stable system. Which I can also write it as omega dash NR dash can be expressed as N0 minus NR E0 minus ES. So that's another way of expressing it. Now what to do? Now what we did in canonical ensemble, what we did was that we did expanded this expression for omega dash nr dash es dash with the help of Taylor series, right? Because that is the way in which you make a modeling of the system, right? You are trying to generate those kind of values with the help of Taylor series. But we need to be more accurate, we need a slow varying function. So therefore we will use the logarithm. Okay. Logarithm. So I hope I need not rewrite the equation for the Taylor series. To remind you, the expression is fx is equal to fa plus f dash a by 1 factorial into x minus a plus f double dash a by 2 factorial into x minus a the whole square plus etc. Here x is equal to es dash and nr dash, right? And a in the Taylor series, a is e0 and n0. If you have doubt, you can go back to the video and which we did for the canonical ensemble. So if when I expand it with the help of logarithms, I can write it as ln omega dash n0 minus nr e0 minus es is equal to ln of omega dash n0 e0 plus dou ln omega divided by dou n dash nr dash minus n0 plus dou ln omega by dou e dash es dash minus e0 plus etc. Right? So that is the expansion in terms of the your Taylor series. So we continue. So this is the expression, and if you neglect the higher order terms, I can write this as the left hand side is equal to, which is ln of omega dash n dash, so that can be written as equal to ln omega dash n0 e0 minus, so we have dou ln omega by dou n dash. So what is that? Dou ln omega by dou n. So dou ln omega by dou n is equal to zeta, right? You go back to some of the initial classes, initial videos. So dou ln omega by dou n is zeta. So I substitute that over there. Then I can write it as I put the minus because I have the nr dash minus n0. So nr dash minus n0 is minus nr, right? So now I express it in terms of the nr itself. Therefore I will get the minus there, and therefore I can write minus theta nr and dou ln omega by dou e, which is what? Beta, right? Minus beta es.